With Chapter 3, which is called Further Applications of Area and Volume, you really need to focus on what's different. Now, much of what you've previously learned about area and volume will come up. However, I strongly encourage you to think about how the questions are now different to just straightforward questions. And in particular, I'm going to focus on the different aspects of this chapter, in that I'm going to start with 304, which is Simpson's rule. This isn't something you've done before, and I'll continue on with 301 and 310 because that's talking about error, which a small amount of that you've done. But really, overall, even when we get to revising area and doing area of composite shapes, I want you to really think about how these questions are different. It's probably more likely that the questions in the HSC will be of the style of the questions of this chapter as opposed to the questions you got in the preliminary course on area and volume. Just because the concepts of area and volume aren't unique to Stage 6 and the HSC course. Some of them were introduced in Stage 4 and certainly Stage 5. And so the HSC then is going to examine the more difficult situations where you could use the area and volume formula. So that's what you really have to be thinking about. So yes, you'll have to know the basic skills for finding areas and volumes, then apply it in more difficult and unusual situations. Okay, Simpson's rule. So Simpson's rule is a rule that is given to approximate area, and then we'll see a variation of it for volume of irregular shapes. Now, up until now, the shapes that you've found the area of have had straight sides, or they've been something to do with a circle. So we don't really have a method for finding the area of an unusual shaped object, certainly one that doesn't have straight sides. Now, this formula doesn't give an exact value for the area either. It will give an estimation of the size of the area. One way in which you can make your estimation of the area more accurate is to apply Simpson's rule more than once over the area. And when I've explained what Simpson's rule actually means, then you will see how we could apply the rule more than once. And more than one application of Simpson's rule is a more common question actually in the HSC. So again, you're learning what Simpson's rule is, but you're also paying attention to the more sort of the extension aspects of Simpson's rule, which will be more than one application and certainly volume. Situations where you might see Simpson's rule actually used is if you're trying to estimate the area or the volume of a lake or a dam, unusual shaped land masses, maybe small islands, which certainly aren't going to have irregular straight sides. So that's where you could actually use this formula. The good thing about it is the formula is on the formula sheet. Please take a moment, maybe pause this video now, get your yellow formula sheet out and identify where Simpson's rule is actually on that sheet. And realise that there is a description. If we look at this in terms of the algebra aspect of the formula, it starts with an A, which obviously would be the abbreviation for the area. You can see a fraction, h over 3. There is a explanation of what h is. It's here. It says h is the height or the width of equal parts. We'll come back to that. That's probably not making any sense to you at the moment, and that's fine. DF is also explained. This stands for 4 times DM, and please be aware of that. Write that on your formula sheet, write it in your notes. Be absolutely aware that you must introduce a 4 there. DM is explained here, and DL is explained down there. So be aware of that. Those explanations are actually accompany the formula on your formula sheet. Okay, so what are they? What are these, especially this 1, 2, 3, 4 values we've got here? A, we know, is the area, but it's these 4 values. Well, let's take these 3 distances. D first, it stands for D middle, and D last. So what actually happens if you've got, say, this unusually shaped dam? Let's call it a dam or a lake. First off, 3 distances must be measured, and this, of course, would be one application of Simpson's rule. So we're going to apply Simpson's rule over the entire lake. So what will happen is, at this distance, well, maybe they'd actually start with this distance here in the middle. So estimate where the middle of this shape is. It's a little bit difficult. Again, all of this is just estimating. So we estimate the middle and we measure the middle distance. Remember, in the formula, that's the one that gets multiplied by 4. Now, there are 2 other distances, and they're measured at some agreed distance or width, meters away. So the important thing is that from this line out to here is exactly the same as from here to here. In the formula, it is called H, and it sits there. So if all up we said, oh, look, this is about, it's about 25 meters long, we might have said then this we'll find the middle and we'll put H equal to 10. So we've got 10 and then we've got another 10, which gives us our 20 meters, and there's this little bit and this little bit, and they're making up the additional 5 meters. So 10 meters from first distance to middle distance, another 10 meters from the middle distance to the last distance. And yeah, usually you don't have to worry about that size, that value, that H value. It's almost always given. So it's already been decided how far apart these distances should be made so that we're getting a fairly accurate approximation. You wouldn't want to restrict your distance and put them too close to the middle, just in case the shape really varies towards the edges. So yes, this regular distance to use up most of the space that you've got is determined, and the distances across are measured. So middle distance, first distance, last distance. So once you've got those 3 measurements and you've been given the distance between those measurements, you substitute into this formula. So it becomes a substitution question. It becomes an algebra question. Substituting into a formula. You can practice this yourself on this diagram here. So you can put your middle distance in and call it the middle distance. Then, some people might say, well, I'm going to make my last distance right over here, DL, and then think about how big that is, and then come back exactly that same distance, and this is your D first. Now, you might say, oh, well, look, they're very small distances, D first and DL, and I think that's going to have too big an impact overall. I don't really think that was a good idea. And you might say, well, to make it more accurate, we could actually do 2 applications. Two applications. So here we're going to have a look at, here in this one, we're going to have a look at doing 2 applications. So it's always best with 2 applications, still to mark the middle. Then this is going to be 1 application here. So we have to have a middle and a first, a middle and a last. Then we double up and we call this again first, middle and last. Now all of these have to be H. They all have to be exactly the same distance apart. And so now you can see that we've got our 2 applications. These, whoops, I'll do that in red. These 3 are 1 application where you'd have D first, D middle, D last. And then we're going to have our second application. And this distance here is going to double up and become D first again. This one will be DM and that will be DL. Now with this third shape, I've set it up such that we could do 3 applications. So you can see I would need 1, 2, 3. That would be 1 application. 4, 5 measurements for our second. 6, 7 measurements. Now let's identify them. So this would be application 1. So this would be D first, this would be D middle, and this length would be D last. For our second application, we would double up with this value, this distance, and call it D first. This distance across here would now become DN, and this would be DL. Then for our third application, you can see this measurement here doubles up and becomes D first. We've got a D middle, and D last is actually a 0. So you are going to get a more accurate estimation for the area. You can see that the size of H is decreasing as you increase the number of applications. So if you can, the smaller you can make H, the more accurate is your estimation. I'll stop the video there and talk about the rest of it in a new video.